Good morning. So, as you know, my job is to just refresh your memory on the theoretical aspect of the topic which Dr. Panda will continue again, its application, particularly in tailing dam design. So here I am starting with the theory part, or I say always in terms of physics, that what is there in physics? First is that flow through porous media. So when I am talking about flow through porous media, there can be different types of flow. Change. Slide change.
You just know the keywords.
Okay. So as I say, so we say flow means water flow I am talking about, but I say there can be different types of flow. Why it has become essential? Because nowadays, as I was talking about red mud, or when we are talking about this BP tailing and so on, the permeability is so low, sometimes we are taking help of other aspect like thermal, electrical. So these aspects of flow also now is being required in some cases to decant or reduce the moisture to help in consolidation. So that way if you see, because the formula is similarly, the gradient is there, a constant and a potential. So that way, so people have tried to make it, so how to make it both electrical and hydraulic. Both can be, if you go for quickly, it can also consolidation, and consolidation is main part. I will come to that. A flow through that through consolidation is important. So there are different laws are available. So physics we are trying to follow when it is not sufficient. Darcy's law is not sufficient. So now think about, now I will come back to Darcy's law. So people see it is an empirical method. He worked some test in a sand, and finally say that when the flow water is flowing like this, there are two different shades over a distance, and then he said it is a gradient, and accordingly he said that we can say the flow will be equal to, depending upon the head. What are that head? Then Bernoulli's theorem said 3 heads, but we say no, here we need only 2 heads, that is pressure head and elevation head. So these two important, how we are building up the pressure. So that part when we are talking about, like someday yesterday was talking about how much pressure at we are putting 7 meters of overloading, then how much will be that pressure. Here the flow is velocity so low we cannot consider it. So this flow also depends upon different factors. Fluid viscosity, because now just a question was there whether your geosynthetic or geomembrane will be effective for all types of leachates. I mean, when I am talking about leachates, means that water coming out of this one. That means why they came to aspect, like one is aspect, is there any reaction? So that way, so leachate once it comes out, it's like Darcy did for water, and here we are talking about that depends upon fluid density. Similarly, pore size distribution, void ratio is not only effective, even the void ratio is same, but how they are oriented, that the people into petroleum industry, they do lots of things on this, whether there is a crack or so, and then the flow will be more than the available void ratio. Grain size distribution, roughness of the mineral, and degree of saturation. These are some of the aspects which the flow depends upon. So it will say this Darcy's law is also very specific. It is only valid for steady state, and then also it will not be available if these are the issues. This particle migration which may cause void plugging or unplugging. Because if the flow is very high also, it is not that condition valid. Like boulder, and if you suppose the water is moving through boulder and very high velocity, then also it is not that laminar flow. So that is value only for laminar flow. So then electrokinetic effects, because hydrokinematics is the next chapter, Dr. Ponda will talk about, and chemical concentration gradient. So these are not depending upon this one. And another aspect you see, internal swelling and dispersion of clay particles also can change in this flow. I'll quickly go one or two examples. So this is how we say that here up to this zone it is laminar flow, which we say Darcy's law is valid. Darcy's law is valid up to this point. Then there is a transition up to this point we can take it, but then after no, it will not be valid. So this will not be valid for non-Newtonian water flow. So that I am not going to complexity, so depend upon the viscosity and flow. So that is Newtonian and non-Newtonian flow. Then blocking and non-blocking, that also will not do it, because particularly when you are using clay liners, using Montemore light, and that time I will just suppose any other leachate is coming which is reacting with the Montemore light, then how it will also change the void ratio. What you are getting in the laboratory will not be the same. Okay, this equation, when this flow through porous media is also both important in terms of permeability and consolidation. I say this is only one equation. If you will see, this is the flow through porous media equation. So I have got two parameters. One is a void ratio, other is saturation, degree of saturation. What Terjagi did, Terjagi agreed that degree of saturation is constant, that is 100% saturated. And the flow is steady. That means nothing is changing with time. Then only Darcy's law is valid, then it comes flow through porous media. But then, there is a case, suppose when I say that it is a compaction, I have done the consolidation. When say consolidation, already flow is, water is saturated, I assume water is saturated. Then I assume putting the load, what is changing? Void ratio is changing. S remaining constant, suppose if I will take it, S remaining constant, this E is changing, so this becomes 0, only this I will go, and this is also 0, I mean sorry, degree of saturation is constant, so this will be 0, I have only this del E by del T, void ratio changes with time. So that is consolidation equation. So that means flow through porous media, consider mathematically it is one equation is there. This is the governing equation. There are two conditions. If it is a steady state flow, then it becomes permeability. If it is unsteady flow, that means the void ratio is changing with time. If it is changing with time, then it becomes consolidation. So now I am going through that, because like said, we compacted with a roller, but the permeability didn't decrease. So now there is one more compactor called kneading action, or that is called seafoot roller. So when I had designed a clay liner, so that I said, the top layer only to be finished with roller, I mean smooth wheel roller, and beneath it should be kneading compactor. Not now, our all earth dams. The core was built with kneading compactor, seafoot roller. So seafoot roller can only, just like a आटा को डाव बनाने के लिए, so you put your fingers. If you just make it, that's very difficult. So this seafoot, or that is called kneading action, it penetrates and give a compaction. Otherwise, in the clay soil or this silty clay soil, it does not behave properly. So now you see, what you want? You want an impermeable layer. When we don't have this geosynthetic, geoliner and so on, we are using only the soil itself as an impermeable layer. So you see, if I am doing kneading action, it is reducing suppose a 2, but if I am going to with static compaction, maximum I can go up to 6 or so. So there are 2-3 times you can reduce the permeability if you are going with the kneading action, if you are going, because permeability means you have to go with the fine grained soil. So that is one aspect. Then, where you will compact it so that how much permeability requirement will be there. What is your requirement? Your strength or permeability? All these clay liners are designed on two criteria. One is the permeability, other is the shear strength. It should not fail due to shear strength, and also it should have sufficient impermeable to protect it. So that way, so you have to also, this laboratory testing somebody has given, he said permeability of this material is 1.3 into 10 to the minus 6, that is not sufficient. At what moisture content is he talking about? Wet of optimum, dry of optimum, at what moisture content you are compacting, accordingly you will get that one. This is one aspect which need to be taken in at the site. Next, suppose say I want to same density, you see, my density I am taking any soil, A, B or C different because you see, needing action I am going for, if I give more energy, more compaction. So where you want, suppose say I want A here, this compaction curve. If I am working, this is my OMC. Just a minute. So this is my OMC. If I am going for dry OMC, you see, so this value will be high. That means permeability will be high. Now same thing if I come to wet of optimum, permeability decrease like anything. So that moisture content, somebody says it is only the OMC empty is not sufficient. You ask the compaction curve and corresponding permeability curve. So if you are getting that only, you will be able to know at what density and moisture content I should compact if my requirement is permeability. So that way, so this if you will say low density, obviously therein I am getting, but here you see permeability I am getting the reduces if I am compacting with this one energy. Next, another one. There is a standard proctor or modified proctor, that roller, 8-ton roller or 10-ton roller or 12-ton roller. So that way, if you are giving more strength, that is also making difference. Again, the particle size. It is a clogging, 19 mm clogging or 4.8, I mean the clog, bada jo geti hai. So what is the size? That will also permeability will change. So for this reason, so that's why what we need, when somebody says OMC, MGD, UCS, permeability, so those one line information is not sufficient unless I interpret my data based on these informations. So you see 19 mm clouding can go up to here, and if I go with 19 mm with a heavy compaction, it will go up here. But 4.8 standard, you see, this is 19 mm with standard compactor, and this is 4.8 with standard, I mean proctor compaction, standard proctor compaction. If I am going to modified proctor compaction with 19 mm, immediately the value increases. So that means then it can properly compact because you need more energy. So if your size is there, accordingly also you have to increase the energy effect, I mean the energy requirement. So accordingly energy can be increased in different ways. So like one is the heavy ton roller and also the number of passes. So accordingly you will only get it. You see here another one. Sorry. So here what happens? This is degree of saturation. If it is 100%, this value is 2 into the minus 7. But if I am getting the degree of saturation is changing, obviously what is happening that the value, I will go with this way. So if you will see this value is further decreasing, I am coming to close to this called zero air void line. So close to zero air void line if I can go for, then I can get better compaction. Yesterday also we are talking about one, like one is called void ratio. If you go for the void ratio, so this void ratio is important for permeability. But when I am saying that if I draw a curve here, that is degree of 100% degree of saturation line or zero air void line, this line is totally dependent upon the G value, specific gravity. Suppose this is a specific gravity 2.6, if I take 2.8 it will come here, and if I go for and so on, it will go this way. So that's why only I was talking about the specific gravity plays a big role in terms of its voids, particularly in the tailings. Now here, nowadays, is it sufficient like doing a test in the permeability, what else say, static permeability or variable permeability apparatus in the laboratory. So that is not sufficient, because what the permeability at a higher pressure, that is important. What I am talking about in the falling head or variable head, I am saying this much of water I am allowing pass through a soil mass, and then only I am saying without any, I am like the gravity, how much water is passing through that. But in actual case, how we are going for? At a certain pressure, I want to find out what is the permeability. So we need to know now that what is the confining pressure. If I will say confining pressure 20-200, so that gives that is a vertical and horizontal. So that is also, what is this? Horizontal is here 20-200, and a vertical, this is also reducing from 20-200 depending upon the molding moisture content, because towards this comes weight of optimum. So that, because many a times we say that K, molding coefficient of permeability, but is it a vertical coefficient of permeability or horizontal coefficient of permeability? By time if in the layer also, if you will see vertical coefficient of permeability is higher than that of horizontal. I mean, if you will go for Darcy's law and so on. But suppose there is a stratification and other things, like we are putting in layers. So that, as if say slimy one layer is there which is horizontally very, coarse grain material is there, so that will make a good horizontal drainage. But then after, below it there is a compacted strong layer with fine grain and it is impermeable. So that way you have to see, and actually Dr. Panda will also tell about this, how this K value is different, then your phreatic line gets changed. So you have to consider both KH and KV. This is what I wanted to add it to. So this is called as a flexible wall permeameter. This generally we don't use for our ordinary civil engineering job, but this is very essential for the tailings. After 3 days, tomorrow evening or sometimes, I will show in the laboratory we have got all these things. So what is the advantage of here? So here one is there only if suppose a toxic interface there, because we don't all this leachate by default, what you are talking about is toxic. So these toxic, while using it, my frames and other things may also may corrode also. Even for this equipment we are not able to use if the water is with high hardness, because some of the things will be deposited with the calcium and other heavy metals. These are not that alkali metals. So for this reason, all these arrangements are there. And what else? You can find out the permeability at what pressure. The constant head or variable head permeability meter only can give you gravimetric. But at the site, when I am pressing it at certain head, at that time what is the permeability? That only can be determined by this, what is called flexible wall permeameter. So now if somebody is talking about permeameter, so you have to give this one. And when I am talking about this, suppose like here, this is one of the thing only I am showing it here, for others I will not go for it. Like you see, I have given 100 kPa, 300 kPa and 500 kPa. Accordingly, the permeability will be changing. This is the permeability. So this is 10 to the minus 4 and it is 10 to the minus 6. So there is a change of permeability with obviously moisture content. Moisture content, weight of optimum will reduce, and this will also reduce with the pressure. So that way it is only not dry up optimum, it should be on weight of optimum permeability if required. And also you have to see that what pressure you can simulate at the laboratory or not. Okay, so this is again, because if you say void ratio 1.3 in one case, suppose it was coming, and suddenly if I make it wet, it reduces to 1.15. But same moisture, just I added, I put it in there, I was compacting, then I put some dry कर दिया, फिर थोड़ा पानी छोड़ दिया, तुरंत settle कर जाता है. So that also happens in many of the tailings, that we think it is already compacted, but it's not really compacted, and once it saturates, again it gets compacted. If you add water. So I will not complicate with this one, but now that's why people on the tailing are talking about unsaturated soil mechanics. That means because you said 20%, 30% water is there in. So it is not a saturated. Terjagi said consolidation is valid only for saturated soil. So how I can apply that in this case? So that way, or maybe we cannot that void ratio what or settlement I am calculating use the simple formula given by Terjagi may not be valid. So this is another aspect when I am talking about that. This is called thixotropy that we are doing for the clay. You see 21 days के बाद भी hydraulic conductivity तुरंत कम हो गया. This is same thing. Only I wait for 21 days, it also reduces. That is another aspect of this permeability. So that means I am trying to just highlight the factors which may affect this permeability. And here this is another one is talking about this simply sodium method clay liner exposed to calcium rich paper mill sludge. So in the what do we do bentonite clay? As a liner. Now only the composite clay liners are coming, putting the bentonite inside, and outside we are providing geosynthetics or geotextiles and so on. So what happens? Suppose I am coming in contact with the calcium mill sludge. So this is what? This is basically the void space in between. You see, this is the void space. If this pore space decreases, then obviously it will reduce. Now suppose this pore space increases, reaction होने के बाद क्या हो जाएगा? Permeability बढ़ जाएगा. So that is another aspect. So that's why that time when somebody was asking if I differently said, these aspects come into there. If you have got a bentonite in that composite clay liner, is it reacting? If it is reacting, then there will be like a soiling. And then what I was talking about Darcy slot validity and invalidity. So these are the cases where you have to be careful about that when you want to use such cases. Another thing for which all these are happening, there is a flow one aspect, but with flow what is happening? The stress changing, for which all these are happening, like what we call it as a static liquefaction or piping failure or whatever you say later on as washed out of the dam. ये just flow ऐसे कर दिया पानी ये आ रहा है. So now suppose there is no flow condition at any point here x, and soil mechanics consider only effective stress. What is the effective stress? Effective stress हो गया पानी कुछ is not flowing. It is only static here because it's same line here. Then sigma b dash equal to gamma dash into z. यहाँ पे निकालेंगे effective कितना होगा इतना. So gamma dash into z. Gamma dash is equal to the submerged unit weight. Okay. Now next downward flow. ये ऐसे इधर पानी आ रहा है, ऐसे बह के उधर जा रहा है. तो we due to this there is head loss. So head इधर से पानी आके इधर जा रहा है, तो head loss हो गया, मतलब downward flow जा रहा है. What happens to the effective stress? If you see the previous slide, it was gamma dash z. Now it has become gamma dash z plus gamma w into iz. Iz is the gradient and z is at what distance you want to find out. Accordingly, the effective stress is increasing as there is a downward flow. But if opposite, upward flow, this you see the effective stress is decreasing. So this is the effect of flow in any tailing dam. That when it is going at the exit point, at what condition it is there in. At exit point it is booking me upward flow or a downward flow. So accordingly the effective stress will change, and this is what we call it as a granular soil में बोलते हैं quick condition, boiling of sand and so on. So this is another aspect when I am talking about permeability, because in consolidation it is related to the stress there I am talking about, because the void ratio is changing. In the permeability generally we didn't discuss that what is happening if there is a steady state flow, but what is happening with the effective stress at different points. So these causes a problem and that is what Dr. Ponda will discuss. And you see, this is finally makes a piping in a dam, and this piping is critically, this is called I mean when it is leaving by, this is critical divided by exit. When it has become 5 to 6, many dam has failed, not only tailing dam, rather earth dam also, or water retaining dams also has failed. So this is an effective parameter called factor of safety against piping. If you don't provide, then it is going to fail. For that, what you need to do? You need to do this filter design. So now this is a common, you see every dam you will see there is at the end they are putting something what they call as a filter. So Dr. Panda will discuss about more on this filter, vertical filter, horizontal filter and sloping filter and all these things. So this is the lifeline of a dam when we are talking about permeability, and due to permeability the change in strength. So that it has got two criteria, one is the retention, other is the permeability. Retention means prevent washing under fines. So that's why filter grain must not be too coarse. And then permeability, if it is must not be too fine, then pani jayega nahi. So now we have to make a compromise between these two. So now based on this, long before Terjagi and they have given some criteria. And in fact we will show an Excel sheet, I think Dr. Panda, I think we have got an Excel sheet. So we have to see this, show this design tutorial, that what you should be the filter. Then only there will be no retention, pani ko rokne se problem hai. So it will not retain, and also it will not allow the fines to pass through this. So these two criteria we call it as, and the fine, this is there, the grain size curve for all filter must be parallel. So grain size curve should be parallel. So this is the criteria. So what I will do, I will stop it here, and I now invite Dr. Panda to continue from the 5. So he will talk about the, so I am now refreshing the theory, so he will tell about the different concept. Okay, so I will just continue some more, because as Dr. Panda has already shared some of the things. So now here some of those who are dealing with operation might be very common picture for them. And you will see now what is this. We have got upstream design. I think design part also has been some already discussed. So what is there? Why it is high permeability? Because coarse grained tailings are stored here. This may not look, exactly that is for those who are dealing with arch dikes. The arch dike, the particle variation is not much, but still those are bottom arch, they will try to settle close to where we are throwing it. And this fly ash will settle away from it, because most of the time we try to connect them together and pop it. So that's why there is not much difference. And then you see, this is another concept which many times in India context we don't follow it. That is your decant tower. So decant tower means what we do now. we have got like in the very first class when Dr. Panda was talking about partition, we like a four, we have got say 4 nearby pond. We make it operational or 1 or 2, then we try to shift it to the other, and this the which was filling, now there we try to settle down these fly ash and decant the water to the next, or we sometimes take it back to our plants. But then suppose that this is like an emergency type of things where if you feel you are not able to manage, particularly the tailing dam has a problem in the rainy season, and that is also in this diagram is there. Suppose many times we don't divert this catchment outside the tailing dam to a nearby water bodies. It enters to the again to the tailing storage. So that is one aspect. Suppose those who have already diverted this water, next comes that the catchment of the tailing pond itself. So when I am talking about that, so now you see here this water flow, this is suppose a level, and now I found this water level is increasing because last time also it might be discussed that where it called the overflow section, and many times it fails in overflow or when people try to make it the pass the extra water, because we say like some top of it I'll make a passage and water should go. That is where we do the mistake, and that initially many times people were doing it in the river flood condition, but with some drainage path like sandbags and other things, then we are trying overtopping but with a caution which is not there in tailing dam facilities. So in that case this is another aspect where we can talk about this decant cat tower system, which is not we are following now, but this is another aspect. And yesterday also one thing, now we are following mostly overflow section with spillway and other, that we have got. But this is another case if you have got a choice. It's not always easy, but if you have a choice only, irritated. Now here comes this water when we are recycling. This is called water balance. This is what we do water balance in the water resource engineering. So if you look at this, how much it is all the water which is coming to this one, that suppose say undiverted runoff, as I said you, if your runoff from the rainwater is not again entering, you are not diverted outside, it enter into the tailing pond. Direct precipitation on the tailing pond, that area. So then what will happen? Some of it will be evaporated and some of it will be here, and again also from this tailing also some there may be some evaporation. But many of these will be in this passing through this tailing, and passing through the tailing dam may come out also, for which we provide a side drain through filter media and allow to collect it. And suppose in this case you can provide another dam here, because that water is your precious, because as a plant you need water. So that water also you can recycle, because you see some of the water will pass through this on ground below, some of the pass through the tailing dam, some of the water will go to evaporation, but still whatever you get it or throwing it to outside. And now when we are talking about zero discharge, that is another aspect where this may help you to provide the another dam to just retain the extra water which is coming out from the tailing dam. This water generally we don't take it. So if that I can take it, then I can process it, do all these things, processing and required treatment, and I can reuse it or send it to somewhere. So this is another called water balance of tailing storage facilities. So this way you can save water. So this is another aspect I will say, if possible, it is also may be considered. But the problem with some of our tailing storage facility in Indian context, we start with our boundary So we have no option to other than going upstream method. And that's why though there is central line method, downstream method, everything is able to do not no choice. We start from the boundary. So that way we lose this aspect when somebody says that water now comes there zero discharge, so then becomes a difficult. So these aspects we are not able to consider. Okay, so sorry, this is it. Okay. So now this is again for same thing as I said you how to collect from different. So here anybody can tell about like any of downstream method or central line method. So many industries people are sitting here. Any of the plant has got this raising particular tailing dam or all it is? Yes.
We have first raising of our ash dike, which consists of both upstream raising some portions and downstream raising some portions.
That is, this is like a central you are talking about. This
not
is
central,
one.
Not central. Upstream raising on west side of dike and on east side of dike downstream raising we have.
I mean, say, suppose there are four boundaries. In one boundary you have done downstream, another boundary you have done it upstream.
Upstream because other two boundaries are surrounded with hills.
Okay. So you don't have an option there, so that's why, and by that mostly that becomes a boundary also. I mean, your boundary also. Land boundary.
Land outside our dike, where we did not get any land, then we go upstream raising. When we got land outside our dike, we go with downstream raising.
Yes, that is the reason. So that's why what I was talking about, why this extra water or this, what I will say, water management of this tailing becomes difficult due to our approach of starting the dike with our boundary. And now many places, one time what is there, upstream method should be banned.
Yeah.
But in Indian context, it is impossible now. All the dikes are upstream method. Because most of the upstream dike method failed, and once upon a time they thought that we'll ban this type of things. Because initially it was the thought of better option, now but unless we treat this, so then it becomes difficult. This soil was loose. So anyway, so now these type of things when I am talking about this, I can use this only if, but otherwise what I will do, suppose in upstream method, my requirement is less here, I don't have any choice, I have to take it from here. Because as I am raising the dike, I should also, one more aspect I should keep in mind. How far this water body should be close to the dike. So that aspect, actually Dr. Pandya has also shown you that how it is what is the idea. In any design tailing storage facility, the phreatic line where it passes through, and accordingly the flow will pass through that line. And basic design, what we say, the water is following that phreatic line, and I will make a add to it the drainage layer, so it becomes weaker. So in these cases, if you will see, as we depends upon this downstream or upstream method, this super liquid or that is the tailings, and suppose in fly ash, the water is not a problem. What about the other tailings? In case of suppose I am talking about red mud, it is toxic also. So that aspect, it needs a treatment. Suppose that is chromium the most. They have got all the time there is a treatment plant near chromite mines. So without that treatment, they cannot allow any water to outside. So for that, this method that is of treatment of the liquid should be also kept in mind when we are going for this type of tailing design. Okay, so this also, if you remember in the very first day we were talking about this based on the hillock. This is basically for metal mines tailing storage, because as I said, in thermal power plant, mostly in the plain terrain or so, there we get rectangular plots to make our ash dikes and do it. But in our tailing storage close to the hillocks, so there you see, so there what we need to do, suppose I have got, this is what I can, depending upon the contours, I need to keep the water, you see here, I am not keeping very close to the this one, I am keeping it here, and then I will try to, if I have got a drainage path or something, I will try to take it this way. So this is again also, last time we were talking about this upper compartment, lower compartment when I have got a hilly terrain. Very first slide if you remember. So that time we were talking about this compartment, the tank storage facility, and same only here I am talking about how to manage this pond or water flow. So this same figure I have drawn it. Okay. So this is what you will start from here, because these further. Okay. So this is what I was talking about, this diagram. Yes. If you look at this one, so this is what, if I can provide, so then we will do it, because this is not a new thing. This also we do in hydropower when you have got a tunnel. So suppose in a tunnel I am putting the water, and suddenly that is called a short shaft. Suppose a tunnel in some requirement and I stop it, water, where that it will go? So it will again push back to the tunnel will be 500, so it will crack it, burst it. So there the opposite way do it. Like here what I am doing, vertically downward I am taking the water, but there I take the water upward. I have put a vertical well there in. When I stop this water, the automatically water will short shaft. That's called a short shaft. It will just rise above the hilly terrain. That should be again within a container. The water should not come out of it. So we put a container and it comes around 10 meter, 12 meter, 20 meter, depending upon the height, whatever you stop it, it will come out. So there it is against the gravity, and here is just opposite. If I invert it, that's why, because we are civil engineer, so I want to try to just correlate that way. Here what I want to do it, gravity, through gravity, if I can take it down. If I have got a provision, and that is, there it is against the gravity, here it is just with the gravity. That is the difference of this. And so this also, if required, then if you can store it and then later on also pass it, that is also another advantage. Like in the short shaft, what we do, it store beam and therefore, then when the tunnel is on, then it passes through. But here what we have no choice, it has gone without effort, but if I want to take it, I have to put some effort. Okay. So this is a reclamace pond. Reclamace pond is there also in some of our like red mud and other things. They have got the reclaimed pond. That means this water, can I pump that water to a pond dedicated for this extra water from which we pump it. In steel industries there, in aluminum industry there, but only we don't use for the thermal power plant. We have got plenty. Sometimes what we do, keep one chamber with the water, other chamber we make it dry, and alternately we are using it. And this also, you see, this all these depend upon also this climate effect. And in when I am talking about Indian context, so these have been so far also being used by different industries, particularly steel and aluminum industry. They have got this pond, reclaimed pond, and they are using it. Okay. This is another aspect which we don't, and for which in the rainy season we are in a mood that we are in apprehension that it may overtop. So this apprehension we need to follow a guideline. So if you see here, there are two types of guidelines. This pond is located out from any perimeter embankment. This is standalone, suppose say. Because nearby pond is not there, this is a standalone single pond. And here suppose say I have got partition. So that is the difference between what is written against perimeter, that is another is there, another is not there. So what is the difference? So first I have to consider the rainfall 1 in 100 years. And if that rainfall continue for 72 hours, then what will, I'll calculate the catchment, runoff, and then the water level. That level is here. Okay? So because this pre-board people take it blindly 500 millimeter or 300 millimeter. But this extra rainfall, now obviously you say, always you say climate change and so on, but if we design this aspect also, it is sufficient. That means whatever the rainfall, that is 100 data, which is the maximum, I will take it. And suppose that rainfall happens for, that is 72 hours, then if, what is the runoff, suppose out of this catchment, it's 70% or 80% or 60% is coming to my catchment, and if that water is spread over the area of this much square meter or square kilometer, what should be its level? That level I will find out. And then we will go for a beach freeboard. In the first slide it was shown what is the beach freeboard. Above that I will put 500. If it is minimum 500, and then it will be 300 is operational freeboard. So this aspect of the dike design is also need to be considered when I am going to avoid the overtopping of these dikes. This is a very common technique, and in this case what is there? So total is no upstream catchment is there, 1000 minimum with upstream catchment, and that is same rainfall I will calculate. This is the pond level and this is the, this is the normal operation level and this is the pond level. So these, because what is there in, we don't have a control on that pond level, because many times now many ponds I have visited at time, it is they are mechanized in the sense, morning in their mobile they show me that you see our water level today in the ash dike is such and such level, and they have such a warning that this is the warning level of the ash dike water level. But that what I will say, operation or the monitoring is missing in somewhere only I found in 2 ponds this treatment is there. In the mobile also, he message in the morning comes that the top level of the water on this pond number 2 is such and such level. So that way you can monitor it. So whether, then with this, so this will show me that this is my pond level. Now suppose immediately I found there is a rainfall sufficient, what I have got? So I have got the option, one is that now again also sluice. Many cases if the dike is big, then there is now they are also decanting water. All modern dikes has no problem. Only those dikes which were built around 20 years before, those days these things has not been taken care of, many design. Otherwise nowadays they have got decant system, they have got taking back the water in the pipe, and they have to also, like this one also I will tell you other way what they have done it. I remember now. So this one, suppose this is my dike, what they have done, just where that all that label, where is the minimum, there they have put this decant tower, and below this they have got a drain, and this plant is around 5 to 6 kilometers away. Through pipeline they have taken it. They have got a pumping station here and pumping back, because this ash dike is around 30 to 50 acres. So just that, so they are also doing it regularly. They are patented 4 parts. So from 2 parts. One part they are decanting, other part they are using. So it is this part in some case, but not this way. They have done it other way. Or there is like a gate. So through that gate they are passing through the underground RCC pipe drain, and then it comes. It is like a pumping station. From that pumping station through pipe they are pumping back to the plant. Okay, so this is an aspect we need to consider, particularly when we are talking about the embankment crest, because this is a major issue in rainy season for most of the dikes. Okay, so like how to, there are 2 aspects here comes, because if you see this diagram, so you see one is here which is coming that runoff which is coming to the tailing pond. if it is undiverted, but I can divert it. So here it is, I have got a option to stop it. You see here. So here I can stop around here. Another control is seepage. These are the two water treatment we need to consider. These are two basic. I will divert from here and capture what is passing through. So how to divert? So depend upon that, then we can divide into two parts. Like if I want to divide surface water control, then I have to do this catch basin, check dam, diversion channel and decant system. And also for the seepage control, we have to go for seepage collection pond, cut-off wall or geomembrane liner. So I'll just show one diversion first. So you see, so this water which was coming as a runoff outside the pond area, it is being diverted away. So this aspect is that, so now you have left it with, this is my suppose a runoff water, just schematically it has been shown, this is the water part and this is solid part and so on. This white part you just take that it is my dike. In plan we are showing it, so that just a schematic arrangement, this is my dike. And then these are the tailings and finally this is the water. So this inside water is different and this catchment water outside is different and is to be diverted. So that how to do it, I can go with a catch basin. That means that water I put it on a water body reservoir, water reservoir for my future work. For that, if it is otherwise I can, if I have got a choice, I can provide a check dam here and I can make a reservoir here, either reservoir in the down or with a check dam I can do it here. Sorry. And otherwise if I have no choice, I am diverting to the natural body, water body, or finally the decant system. I can problem from there itself, I will capture it and take out because it is not in the pond. And for the seepage control, if it is not hazardous, what we say, then if it is hazardous, obviously I have to collect through a seepage collection pond. In this seepage collection pond, if you will see, we may need again a dam. You see here, this is a seepage collection pond I am going. So I am capturing all my seepage through this and storing it here. So this is called seepage collection pond. For this I can make this arrangement depending upon the type of leachate or water which is coming. Is it too hard that I cannot allow anything to go out? Either I can make it impermeable dam or whatever. So this depends upon the leachate which is coming out. Then the cut-off wall. Already cut-off wall, where we provide? Why we provide? You see, suppose now this water here telling dam, this water is passing through and very close to it. What is a cut-off wall means? If I put a cut-off wall here, suppose say, so something, and like I am trying to, if I go that, if I don't so, my seepage line will pass through a longer distance. So as it passes through a longer distance, my exit gradient decreases and also obviously seepage becomes low. So that length increases. So that is, or else here also, suppose say, if I have got something, that is one here I can provide, which become very difficult because in telling them we don't do it. Else here at least I can make a cut-off wall. Suppose say I want to not allow this water to go beyond certain point. Suppose I have got something facilities here. What will happen now? The water, if it passes through, seep through it also, it will pass through and may be coming out there. So that is cut-off wall is basically to increase the length of the flow line. Okay. Then the other one is the geomembrane liner. So geomembrane liner, suppose say here I provide geomembrane. Okay. I have seen here, suppose say some people who have got a small pond, what they have done, they have provided geomembrane liner throughout, like this. But that is a small pond, what is 110 meter by 40 meter. But what has happened over the years, over the geomembrane, they have only provided the stones, boulders. No protection other than, or they might have protected with the sand or soil, which now it is not there. So it was visible to outside. That means there is a geomembrane. So just to check it, whether that geomembrane is working or not, so I said that you make a, the piezometer. I try to tell them that install 2 piezometer. Just to check, like here the water level is known to me inside. I am putting one here and the other here, away from it. Because when it is exposed to outside, what has happened inside I don't know. But how I will know? Only if there is a seepage through this. Then I found that there is no correlation, because why I put here 2 piezometer, just to draw a phreatic line. Suppose if I tentatively draw a phreatic line, how it passes through. That's why I need, so when you are talking about yesterday piezometer, at least the same line, at least 2 piezometer. Otherwise very difficult to know how the flow is going on. Then from this, because the problem was here, the water table was here from outside. That level is being maintained here rather. And this is not, no relation with the internal. So that way I could know, that means that the geomembrane, what they have provided is still working. Otherwise outside from the side it has been exposed. So I think you can better tell how to protect them now, because now after 10-11 years it has been exposed. It is not covered from the side. Inside I could not see it, so that's why my job was there to just to check whether there is seepage, and accordingly to phreatic line to try to draw that whether it is going that way or not. So geomembrane works, but this aspect also need to be considered when I am talking about like geomembrane liner. Okay, because if there is a really, it's there and it is water seepage would have been there, my phreatic line I could have drawn it and see that it's matching. That means that geomembrane is not working. But here it didn't show me that trend, rather it's showing me the water level at the outside. Okay. This is what is there, because this aspect, when you are talking about this course is geo-environmental, also it is more important. Another important point is that how to use that water. So for that reason also we need to provide this check dam or diversion, that catch basin or so on to store water, because we want to recycle and reuse. Okay. Another aspect, okay. When I am talking about design, this is for the design purpose. When I say that these are the things to be designed, whether it's all these things, so what should be the criteria or the parameter? Like suppose Dr. Dipto, can you throw some light on it, or so far you have not involved in this? Okay, so like when because this standard is available in Indian American context and so on, so that's why I thought in Indian context if something is there in this is nothing to do with, because this has to be customized. This is available on that, and this aspect when you are because every climate, this is a climatic criteria should be considered. So here when I am talking about, so anyway, so this you need to find out. Suppose for permanent diverse channel, what you have to consider, 100 years term event period with 24 hours term, and suppose say that area is 136, example we are talking about, that may vary. Then we have to peak flow design for temporary diverse system during construction, that case 10 years. I don't catch 100 years period, I take 10 years, 24 hours term, and generally suppose say 90 millimeter. Many of design in Indian context we do 90 millimeter. and then flood storage if I am going for, so then maximum precipitation whatever, then half of the probability of it, and then it is 240 millimeter precipitation. Accordingly I will go for a flood storage. So these are the design aspect of the stormwater treatment, or sorry, stormwater management of a tailing dam. So when I am talking about this aspect, I will say take home. This aspect you should always check in after you return back also, that whether my dike, whatever a job given to me for operation, is satisfying this criteria or not. So whatever the standard they might have given while designing, depending upon the design report who was submitted, this aspect you check it whether this water balance model has been considered or not. Because many times, because zero water discharge came in 2010 or 2011 in mining. Before that, this aspect was not there in Indian context. Now they have said that you have to make it zero discharge, and as much as possible you can go on groundwater recharge, but you have to, you don't throw away from your own campus. So that aspect has come in. Then design of drainage feature, like I said, what is the criteria that has been considered. So if I know all these things tomorrow, so I will be prepared that it was designed for suppose a 130 millimeter. I came to know that this last 2 days if the rainfall has happened so much millimeter. So I will be able to know where I stand, where my design stand. So that aspect, so that's why only, though we are not designing anything as an operation engineer, but we should know the design, how, on what basis it has been designed, or what is the criteria they have considered while going for the design. Many times we ignore it because we say these are the things. So that's why this is one only the guideline what we got, Dr. Panda has given. So from USA standard we got it. Then this is finally surface water hydrology. It is this aspect. Actually, they say that catchment area, because this is another aspect in mining. Mining, there is nothing called static. It is all dynamic. Today you have got a dump here. Tomorrow you go there, that nearby that dump is closed. Another they have started mining. Totally the features get changed. What I found, and suppose in one waste rock disposal system, after 1 year when I went, I was searching for where is the dump. So that drainage system is all lost. They have put a pipe, garland drain, then that what they call it, the siltation bed tank. A siltation bed also provided, that when this all these boulders were coming down to store that siltation, then from there we are diverting the water. All that is filled up, and I mean above that is a dumped also. No siltation chamber is also there. Particularly tailing is different, and particularly those when are dump sites. Dump site is still more difficult because that is very dynamic system. So when we are talking about here also, there if suppose somebody is dealing with that type of work also, that is important. This aspect, because many times we say it is a dynamic, only 1 year this mining will be put out, then our drainage system will be changed. But this aspect we need to take care of, particularly drainage for the present, how to divert water, and what is the freeboard requirement if you have got for the tailings. And this aspect for, I will say, this overwater dumping also. Okay. This is, here I was saying the surge, you see leak and rod surge. Here opposite surge, there we say surge tank, here it is a handle surge. That means extra water which is coming out. Then in the pond management, the decant should be able to effectively size and location of the minimize stability to the dikes. So this aspect, I will say maybe we can think of while doing for the retrofitting. In some case it may be possible, because otherwise it's already all constructed, or for new construction it may be considered. Otherwise it's not possible to provide for such there. And suppose when you are talking about when you are talking about pond contingency plan, this aspect also we feel in the sense we don't have any procedure. Like after GI stay maybe, suppose it overtops, we don't know what we have to do. I think some engineer can throw a light. Suppose say there is overtopping. What is the procedure manual for your organization or for a system anywhere? Is there any system? Like suppose there is overtopping, what to do? As an operation engineer, what should be my role? Is there any manual or no? Because I know it is sometimes we don't tell all these things. So this also, now a GI team has all these operations, all these manuals.
We have an emergency preparedness plan for that.
Okay. But that prepared plan for this like evacuation? That's what I said, that is settlement, rehabilitation, evacuation. But coming to this technical engineering aspect, like how to manage it is not there. So that is only administrative aspect, that evacuation and so on. That we find out how much area it is expected to do, and in that area we evacuate people and so on. That is administrative. But technically procedure also needs to, suppose in case comes, how to manage it. Okay. Suppose say this barge, so suppose say if you are doing a barge, decant barge, then in case, that means this you have to do with floating and then you have to pump it from there. Then you have to pump it from there. So this we can try in some some tellings is possible, because this is like what we do, like a pontoon bridge. Like means we have, suppose today the water is there, tomorrow the water may come here. So my decant pipe, I can put a pipe there, from there I can take it also outside and decant it quickly. That is also there, but that depends upon the position and so on in the site may possible, but this is a good aspect when you want to keep it for the future design. Okay. Okay, so this you will start it with the drains and other things, because this is what I just say about filters. So now I will continue. This is very important for the safe design of a dike.